All right, so for this week in Organic Chemistry Lab, we're discussing mass spectrometry. So it's not to be confused with mass spectroscopy. So spectroscopy is a term used to describe the interaction of matter and electromagnetic radiation. And then spectrometry is more so the measuring of atoms or molecules. So here on the left, so I know this is a very complex instrument, which we'll talk about, but this box right here, so this enclosure here is what a mass spectrometer looks like, or it's what a mass spectrometer can look like. So it's not very interesting superficially, it's just a box. And if you can see here, it says single quadrupole mass spectrometer. So that's how you know it's the mass spectrometer. And basically what it consists of is a device used to ionize molecules or atoms. So in this case, molecules. It ionizes those molecules by shooting them, by bombarding them with a beam of electrons. And then those electrons, by bombarding it, convert the molecule into an ion. And then that ion can be measured by the internal workings of this instrument, which we're not going to go into great detail into. But suffice it to say, this instrument will measure the mass to charge ratio of molecules, and then it will use that mass to charge ratio to infer the mass, how much it weighs. So this portion is the mass spectrometer. Now, the entire instrument is called a GCMS, which stands for gas chromatograph mass spectrometer. So on the right portion here, this box is a gas chromatograph. And when we talked about chromatography, we talked about separating molecules based on their affinity for a stationary phase. So in the case of TLC, the stationary phase is basically a plate or a piece of paper. In this case, the gas chromatograph has a very long, thin column. So it's a wound column. Imagine a very thin tube. It's about 20 or 30 meters in length. And that column sits in this box here. So the way this instrument works is you take your molecule that you want to take the mass spec of, or a mixture. In this case, that's the beauty of a gas chromatograph. You can separate mixtures. You take that mixture, and then you inject it here in the injector, and then that mixture will be separated in the gas chromatograph. So chromatography is for the separation of molecules. Okay, so after the molecules are separated, they're going to enter the mass spec. There's a little bridge here where it goes from the end of the column into the mass spec, and then it's going to measure the mass to charge ratio. Well, first it will ionize the molecules, measure the mass to charge ratio, and then plot that data in a spectrum. And then that spectrum is generated on the computer to the right. So the key takeaway here is that this portion, the gas chromatograph, separates mixtures, and then on the leftmost portion, the mass spectrometer, which is the greater emphasis for this video, is what's going to measure the mass to charge ratio and subsequently the mass of the molecules. It's very loud in here because this mass spectrometer works under a vacuum. So there are several vacuum pumps in here that keep this system under a vacuum. All right, so now we're going to go take a look at the second form of mass spec we have here at Chaminade, and that's in the other room. All right, so now we're in the other lab, Lab 0, and this is the room that houses the LCMS. So LCMS is similar to GCMS. So instead of gas chromatography mass spectrometry, this is liquid chromatography mass spectrometry. So just as before, there are sort of two main modules. So the left system is the LC, the liquid chromatograph, which we'll talk about. And then the one on the right is the one we're more concerned with, which is the mass spectrometer. You'll notice this is very much a larger mass spectrometer. It has a much larger footprint because it's a older instrument. So in gas chromatography, gas was used. I didn't mention it, but gas was being used to push the mixture through a column. So in that case, the gas was probably helium or hydrogen and sometimes nitrogen. In this case, we're using liquids. So on top here, you'll see some aqueous solutions. So there's water and methanol and perhaps acetonitrile. And these liquids are pumped through the system. So up here is a pump, and that pump is going to push a mixture through a column. So this here is the injector. There's a little robot arm that picks up the sample. So it has a needle in it, and it draws up some of the sample, and then it's going to inject it. It's not very easy to see, but there's a little plate here where it injects it into the fittings here, into the piping. Here's the little capillary tube where the mixture travels through. You can see it's very thin. Okay, so the mixture is injected. It's being pumped through, and eventually it's going to enter a column. Right now there's no column on the system, it's just the piping. But if there was a column, so it would look something like this. So as opposed to a GC column is perhaps 20 to 30 meters in length, so it's quite long and thin. An LC column is very wide and very short compared to it. So in here is a stationary phase, like in TLC, and that stationary phase is going to separate the mixture as it's being pumped through it. So the mixture will enter, say from the left side, like right here. It will travel down the column and it'll be separated, separated, separated. And then you'll have pure compounds, pure molecules exiting at this side of the column. And then after that, it goes back into the system, and then it actually measures the UV of it. So that's another advantage of LC. This LC is that it measures UV absorption, kind of like in TLC. Not super important for our purposes, but after it enters the UV detector, it exits and then enters this transfer line, this red piece of tubing, and then it enters the mass spectrometer. And this is where it's going to be ionized and then measured. The biggest difference between the GCMS mass spectrometer and the LCMS mass spectrometer, at least this mass spectrometer, is that the GC mass spec is a hard ionization technique. It uses what's called electron impact. So that's when the atom is bombarded with electrons. That results in the formation of fragments. So instead of the molecule staying together, some of the molecules are going to be fragmented. So it's not going to be the whole molecule. This mass spectrometer uses something called ESI, electrospray ionization. And it's a so-called soft technique. So it's not going to fragment the molecule. It's much more gentle. So you don't really see fragments in your molecules here. We have a sample spectrum that we pulled up for you on the computer. So here you can see is a reference spectrum. So this compound is, whatever the compound is 540.1 mass to charge ratio. So on the x-axis, going from 0 to 900 in this case, is the mass to charge ratio, m over z. M stands for mass, z is charge. So in most cases, most ions, whether it be in GCMS or LCMS, and provided the molecule is small, so in the purpose of for organic chemistry lab, the molecules are small, z is usually equal to 1. So it's not a big number. If z is equal to 1, then the m, the mass to charge ratio, m is always what it is. So anything divided by 1 is itself. So we don't have to worry about, charges dividing the mass in half. So if it says 540.1, the mass it's measuring is 540.1. You can see there's a little bit near the baseline, so the sample might not have been completely pure. And these little peaks here are usually sometimes referred to as blades of grass, and you can even zoom in to see the more detailed spectra. So you can see that this molecule may have different isotopes in it, may have an M+1 for carbon-13 or such, or depending on the atom. Okay, so that just gives you an idea of what the mass spec is measuring. On the y-axis, by the way, is the intensity. So that's measuring how much there is of each ion. So in this case, 540 is the most abundant ion. And the most abundant ion is called the base peak. So it's whatever the tallest peak is. The peak farthest to the right, which will be the highest in molecular weight, is usually the parent ion, the molecular ion. In this case, the base peak is the molecular ion, because it's the largest peak, but it's also the farthest to the right. There's some background noise here, but that's not too concerning. So the fragmentation patterns on there will look much more complex in your unknown samples, because those were measured using electron ionization techniques. So those will have fragments, whereas this spectra does not. Anyway, thanks for watching, and we'll see you next week.